Hockey is a game of speed and motion. The team that wins is the one with players who control motion the best. The motion of their skates, the motion of the puck, and the motion of their bodies. We're going to take a close look at this game and some other activities to learn some things about motion itself. All motion obeys a set of physical laws, whether it's fast and bold or small and delicate. These laws were observed 300 years ago by the great scientist Sir Isaac Newton. They can be described in 3 simple statements. Newton's first law says that an object at rest stays at rest unless a force acts on it. And an object in motion stays in motion unless a force acts on it. Newton's second law of motion tells us that an object's acceleration depends on the mass of the object and the amount of force applied to it. Newton's third law tells us that forces come in pairs. Every action has an equal and opposite reaction. Now let's take a closer look at the first law. It takes a force to make something start moving. If an object, such as a puck, is not moving, it will stay at rest until a force makes it move. And once it's moving, it will keep moving in a straight line at the same speed until a force makes it change. This characteristic, or an object in motion stays in motion, is called inertia. Because of inertia, anytime you see something slow down, speed up, start, or stop, you know there must be a force acting on it. Often you can see the force, a push or a pull. Some forces that operate on most objects are not as easy to see. One example is friction, which results from the rubbing together of 2 objects. Without friction, this player or this puck would go on forever. This puck is slowed down by rubbing against other things, such as the ice or even the air. This is friction, one example of a force affecting an object. Friction makes your bike slow down. That's why you have to pedal to keep it moving. And when you want to stop, the friction of your brakes slows the wheel. Everything that moves on Earth is affected by friction. Friction with the water makes boats slow down. Friction with the air makes birds slow down. It also enables them to fly. And friction between moving parts would make machines slow down if more force didn't keep them moving. This is friction. And so is this. There's another force that acts on all motion on Earth. It's called gravity. Gravity pulls everything toward the center of the Earth. It's one of the forces that acts on all objects. Here's an example of gravity. This also is an example. And here's another. We've seen that it takes a force to change the motion of an object. But how much will the motion change? That depends on a couple of things. According to the second law, it depends on the mass of the object and the amount of force. Scientists have some special words to describe this law. Instead of talking about an object's size or weight, they use the word mass. Mass is the amount of matter in an object. a bowling ball and a softball have different masses. And mass is related to the weight of the object. If one thing weighs more than another, we say it has more mass. This is true no matter how large the objects are. Acceleration is the word for a change of motion. Acceleration doesn't mean speed, it means a change in speed. When something that is standing still starts moving, that's acceleration. It's also when something that's moving at a steady speed goes faster, or when something that's moving slows down. Mass, force, and acceleration are all related. When the same force is applied to two objects of different mass, the one with less mass will accelerate faster. If a large force and a small force are applied to objects of the same mass, the larger force makes the object accelerate faster. If the same amount of force is applied to two objects of the same mass, they will have the same acceleration. You can experience this easily. A small car can be moved with a small force. Something big enough to ride on requires more force, and it takes a lot of force to move a real car. Newton's third law tells us that forces come in pairs. Every action has an equal and opposite reaction. Here's one way to get a feel for that. If you were sitting in something that could move very freely, such as this kayak, and you threw something very heavy, like a shot put, you'd go backwards. And that shows Newton's third law. Here's that law again. Can you see the reaction? The stick sends the puck flying. Is there an equal reaction back against the stick? Yes, when the stick hits the puck, it exerts a force in one direction. The puck exerts an equal force back against the stick. You know the force is there because you can feel it in your hand. Newton discovered this law by watching his cat. Can you see the equal and opposite reactions? The cat pushes the ball backward, and the ball pushes the cat forward. A rocket is a good example of the third law. As hot gases are pushed out the back, the rocket is propelled upwards. Action, reaction. Space is a good place to observe Newton's laws, because as you can see, gravity doesn't affect things as it does on Earth. Here's a good example of the first law. Things at rest stay at rest, and things in motion stay in motion until a force makes them change. For humans to conquer space, they had to master Newton's laws. They had to know just how much force was required to move objects of different mass. And they had to understand how an equal and opposite reaction could send an astronaut floating away from his spacecraft. Motion. Think of some of the many ways you might experience it. While skating, on a bicycle, in space, watching a clock, skiing, running, or bouncing a ball. Let's look once more at the three laws. First, an object at rest stays at rest unless a force acts on it, and an object in motion stays in motion unless a force acts on it. Here's a good example of the first law. Second, an object's acceleration depends on the mass of that object and the amount of force applied to the object. Here's that law again. Third, forces come in pairs. Every action has an equal and opposite reaction. Here's one way to get a feel for that. These three laws govern all motion you can see, whether it's on Earth, on the Moon, or anywhere in the universe.